We'll see if that works out. But so I'll be talking basically about two different topics. The first topic is a suggestion for a technique for how to observationally search for light rays that get bent by large angles as they pass near a black hole. So we've currently never detected such rays, but they're predicted by Einstein's theory of general relativity, and the question is how to actually attempt to realistically detect them in an astronomical system. And then the second part is I'll tell you about what is meant by this phrase, the wave function of the universe. And there is this famous proposal in the early 1980s by Stephen Hawking and Jim Hartle for a mathematical formula for the wave function of the universe. And I'll tell you why that idea is, why I think it's very beautiful, but also why it almost certainly can't be right, and a proposed alternative that hopefully keeps something of its the spirit of that original proposal, but fixes the main technical problem with it. Okay, so let me just, with that, move on to part one. So this is about a paper that came out on the archive. I don't know. Maybe for non-physicists, this is the www.archive.org, the website, and this is the marker on that website for the preprint that we've posted there. This is work done in collaboration with Matt Russo, who is an undergraduate student who was working with me at the Canadian Institute for Theoretical Astrophysics. So what is the idea? Well, so Einstein's theory of general relativity predicts that when matter is present in space-time, that it curves the space-time around it, and that when light rays travel through that curved space-time, that they're bent by the curvature. And this effect is called gravitational lensing. And so if you take an optical telescope and you point it, you take a picture of a rich cluster of galaxies, because of this gravitational lensing effect, you get images like this, where most of these blobs are galaxies in the cluster that you're looking at, but then some of them, like this, for example, or it may be hard to see this one. It may also be hard to see this one. There are some very thin, very stretched out arcs on the sky, and those are not those are not galaxies in this cluster. They're galaxies far behind the cluster that have had their images distorted and stretched out on the sky by this gravitational lensing effect. But even in these very dramatic so-called strong lensing systems, the actual rays that you're looking at, the individual light rays, have only been bent by a tiny angle. They've been bent by much, much less than 2 pi. But on the other hand, as I mentioned, general relativity predicts that light rays that pass very close to a black hole get bent by much more than 2 pi. And in fact, they can be bent by arbitrarily large angles as they wrap around the hole before proceeding to the observer. It turns out, interestingly, that the first paper to really point this out and work out this idea in detail is by Sir Charles Darwin in 1959. This is really a great paper. This is the grandson of the Charles Darwin who discovered evolution. And in fact, he, at the time of this paper, this was I think his last paper. He was in his late 70s when he wrote this. But it's really a very beautiful paper. Anyway, so what this figure is showing is that if I have a source here and it sends a light ray to the observer, well, this ray that gets bent just by a little bit, that's the ray that is responsible for the gravitational lensing effect that I showed you on the previous slide. This sort of gravitational lensing has already been observed. But then the prediction is that there's another ray that passes closer to the black hole, wraps by 2 pi, and then goes to the observer, and another one, the j equals 2 ray, that wraps by 4 pi before going on to the observer, and so forth. There's an infinite series of such rays. And to give you another sense of what's going on here, let's imagine looking at this system face on from the perspective of this observer. Okay, so now imagine we're the observer and we're looking directly at this black hole, and the source is directly behind the black hole. So what do we see? Well, the j equals 0 ray, all the different j equals 0 rays are bent by a little bit and then converge on our telescope. And what we see is a big ring around the black hole. This is the so-called Einstein Ring. And the very stretched out images that you saw on this picture were nothing but but sort of large swaths of approximate Einstein rings. Okay, so that's what the j = 0 ray does, but then the j = 1 ray here produces another ring that's inside the previous one, and the j = 2 ring is inside that, and the j = 3 ring, and so forth. There's an infinite series of rings that pile up closer and closer to the horizon of the black hole. Observationally, this ring is very far from the black hole. You can actually resolve it on the sky. These rings all have radii that are comparable to the apparent radius of the black hole in the sky, so they're extremely small. So the question is now, that's a good lead-in. The question is, can we observe somehow? Is there some detectable imprint that we can realistically go after of these highly bent rays? And so a skeptic would say, absolutely not. Okay? The skeptic would say, and to see why, let's just work out the relative brightness of the j = 0 ray and these j = 1, 2, 3, etc. rays. So the skeptic would say these rings are just absurdly dim relative to this one. You're never going to observe them. So why is that? Well, to make a long story short, to calculate how bright these images are, the key input you need to know, there's a standard theory of gravitational lensing, and the key input you need to know is what is the deflection angle, alpha, that a ray experiences as a function of the impact parameter, as a function of the impact parameter b, basically the perpendicular distance of closest approach to the black hole. And so in the regime where the ray does not get too close to the black hole, Einstein worked out the answer back in the 1918 or something, and it's this famous formula that it's 4 times the mass of the black hole divided by the impact parameter, which I'm doing what general relativists always do, which is setting Newton's constant and the speed of light equal to unity. So this is actually a dimensionless quantity, and it's tiny because the impact parameter in the case where this formula applies is much larger than the radius of than the mass of the black hole, which is basically its Schwarzschild radius, basically the size of the black hole, which is very small. Okay, but then Darwin worked out the formula that corresponds to this strongly bent case. When the bending ray is bigger than a radian, you have this alternative formula. And in any case, plugging these into the standard formula of gravitational lensing, you get this result. This is the mu sub j is how dim the jth ray is, the jth highly bent ring is, relative to the j = 0 ray, relative to the bright Einstein ring. And so the skeptic says, look at this factor. It has in the numerator the mass of the black hole, in other words, the Schwarzschild radius of the black hole, which is tiny. And then these 3 other factors are the distance. ds is the distance from the source to the observer. dl is the distance from the lens to the observer. And d source lens is dsl is the distance from the source to the lens. So those are huge astronomical distances in ordinary gravitational lensing. And so the Schwarzschild radius of the black hole divided by these astronomical distances is an absolutely stupendously small number. And so it looks like this formula says that you're dead. You're never going to, these highly bent rays are too dim. But on the other hand, we can see how to fix that problem. What we need to do is not look at the ordinary gravitational lensing configuration where everything is very far apart. Instead, we want to find some astrophysical system in which the source is very close to the black hole, preferably only about 1 Schwarzschild radius away from the black hole. But fortunately, nature has been kind to us and given us such a source, because almost every astrophysical black hole is surrounded by an accretion disk, a pancake of matter that's falling onto the black hole. And the inner edge of that accretion disk, it turns out, emits like crazy, and is indeed roughly 1 Schwarzschild radius away from the black hole. Okay, so if we make all of these capital D's comparable to, if we make D source lens comparable to M in that way, that is, we bring the source close to the hole, then this factor is of order unity. We don't have to worry about it anymore. But the skeptic is still not satisfied. The skeptic says, okay, Very clever, but you're still dead because of this second factor. So this second factor says that every time a ray wraps by an additional factor of 2 pi around the black hole, that its brightness is suppressed by a factor of e to the minus 2 pi, which is about a factor of 500. So every additional wrapping you want to do, you pay a huge cost. The corresponding image gets dimmer by a factor of 500. And that's a more general thing about strongly bent rays, that if you want to bend by an extra angle chi, the brightness is suppressed by e to the minus 2 pi, e to the minus chi. Okay, so that sounds bad too, but we can't completely get rid of that effect, but nevertheless we can mitigate it a great deal by, again, looking at a different configuration. Instead of the standard gravitational lensing configuration, which is in this straight line, we want to instead look at a right angle configuration like this. So again, we've brought the source very close to the black hole, and now we want to have the source, black hole, and observer make a right angle like this. Because now the subsequent rays wrap in opposite directions, in alternating directions around the black hole. So, if you look at this diagram, you can convince yourself that each subsequent ray only wraps by an additional pi instead of an additional 2 pi. And so e to the minus pi is the price you pay, and that's only like 1 over 20, which is not nearly as bad. That's getting into the regime where we're talking about astrophysical realism. Okay, but the skeptic is still not satisfied, so he says, fine, maybe these higher order images are not too dim to detect, but they're still, the radii, they're still at a distance away from the black hole, which is comparable to the radius of the black hole. And it turns out that there's really only 1 or 2 black holes in the whole universe whose apparent radius on the sky is big enough to be resolved by a realistic astrophysical telescope. And even there, it's extremely hard thing to do. So the idea of trying to resolve these different very dim images around the black hole just seems absurd. And so again, that's true, and we don't want to do that. So the final response to the skeptic is, well, we're not going to try to image these things. We're not going to try to take a picture of these highly bent rays. Instead, we're going to look for their effect in the light curve, the intensity as a function of time coming from the black hole. So in other words, imagine that this source is, instead of continuously emitting, emits a flash. First, imagine that for simplicity it just emits a delta function flash. So what this observer will see is, well, first they'll receive a bright flash that comes this way, but then a little bit later they'll receive the same flash, but a little bit later and a little bit dimmer because it came around the back of the black hole. And then they'll receive the same flash again, a little bit later and a little bit dimmer because it wrapped this way, and so forth. And so what we want to do is predict what is the pattern if a flash is emitted, or more generally, if a time-varying signal is emitted near the black hole. And again, time-varying signals are routinely emitted right near the black hole by the inner edge of the accretion disk. What is the pattern of delays and dimming of the subsequent copies or echoes of that signal that the observer will receive? Okay, so that's what we want to work out. And the final thing I want to say is that for simplicity so far, I've been talking about the black hole as if it is non-spinning. But in fact, most black holes are spinning, and in fact are highly spinning. It's very plausible that many astrophysical black holes are highly spinning, and there's some evidence to that effect. It's actually a controversial issue. But in any case, we are interested in spinning black holes because it turns out that if you make a black hole spin rapidly, that the accretion disk approaches much, much closer to the black hole. It gets very close to the black hole, and so you get an extra boost. Remember, we wanted to bring the source as close as possible to the black hole, and it turns out you can do that best when the black hole is highly spinning. So that's what we want to work out. What is this pattern of delaying and dimming in the echo flashes for a spinning black hole? And that's what's shown in this figure. So basically, here I've on the x-axis in these figures, what I'm plotting is the spin of the black hole. It turns out that a black hole has a minimum and a maximum spin. It can spin anywhere from 0 up to its mass in units where its mass squared, up to 1 in units where g is equal to c is equal to the mass is equal to 1. So anyway, there's a maximum spin, and that's what the right side of these figures represents. And so here, what I'm showing in this figure is what is the delay between the initial j equals 0 flash and the subsequent j equals 1, 2, and 3 echoes. And anyway, you see the delay is it decreases slightly as you make the black hole spin more faster and faster, but it doesn't depend too strongly on the spin of the black hole. Basically, if you put in numbers here, if you talk about a stellar mass black hole, a black hole that was formed by the collapse of a massive star when it expended its nuclear fuel, then these delays are roughly a millisecond. And so what you're talking about there is people observe emission from near stellar mass black holes with X-ray telescopes. And there are X-ray telescopes, there have been X-ray satellites that for the past 20 years have been observing such systems and collecting data from them with time resolution of 10 microseconds, or much better than a millisecond. So one possibility is to look for this 1 millisecond blinking signal in those systems. On the other hand, there are supermassive black holes at the centers of essentially every galaxy in the present-day universe. And those supermassive black holes range from about a million times the mass of our sun up to 1 billion or even more times the mass of our sun. And so for those systems, this delay, if you plug in the numbers, for a million solar mass black hole like the one at the center of our own galaxy, the delay is something like 90 minutes between subsequent flashes. And for a billion solar mass black hole, it's about a day. Okay, so these are all in the realm of realism. None of these times are too small to be detected or so long that you would have to live longer than a human lifetime to see these subsequent flashes come along. And then this figure shows how bright the j equals 1, 2, and 3 images are. The j equals 1, 2, and 3 flashes are relative to the j equals 0 flash. And basically what it's showing is that they get much brighter, what I was saying, that because the source gets much closer to the black hole, as the black hole spins faster and faster, the corresponding echoes get much brighter relative to the j equals 0 primary flash. A particularly interesting case from an astrophysical standpoint is this spin of 0.85. So not maximally spinning, but rather highly spinning. In that case, it turns out that, so you receive the j equals 0 flash, the first flash, and then relative to that, the next flash is only a quarter of the brightness. So it's still really quite bright. And then from there, the subsequent flashes are all suppressed by this factor of e to the minus pi, so 1 over 20. So this flash is about 25% the brightness, and then this is about 2%, and so on. This first factor isn't exactly 120, but anyway. That's the takeaway point, that the echo flashes are sufficiently bright in this scenario and sufficiently and spaced by an appropriate amount that you can realistically hope to go after this signal with an astrophysical telescope. Yeah. Okay, and so here I'm just showing another picture of the effect. So imagine that the black hole, that the accretion disk near the black hole emits this Gaussian blip. I don't know if you can see this, the red dotted curve here. There's a Gaussian, and then it just drops to 0. Then the actual observed effect, the actual observed signal, is predicted to be this thing. This is the first echo. This bump is the first echo flash. Then this bump, I don't know if you can see it, is the second echo flash. It's only 2% the height of the original flash. So this is if you're lucky. If nature is really kind to you, it'll give you a system where you really get discrete, very bright flashes from right near the black hole, and then you get to actually see by eye the flashes in the echo flashes in the observed light curve. Probably, if any such systems are out there, someone would have spotted this by eye already. So to be honest, as I'll explain in a minute, I have not done a thorough search, nor anyone has. So this paper was again just proposed a few 2 months ago. So the search for this signal has not been done, and there's a variety of places you might look. But I personally would love this to be the case, but I'm skeptical that there's any astrophysical source out there doing this. But the nice thing is that a nice bit of sort of confluence of mathematics and astrophysics is that it turns out that if you have a black hole, and it's, if you imagine the black hole spinning around my thumb, astrophysically, it turns out that black holes, when you try to view them edge on, more or less perpendicular to the direction of the spin, they tend to be obscured by dust. So you can't really see the inner edge of the accretion disk. The ones where you can really see far into the black hole, see emission coming from right next to the black hole, are ones where you're seeing them nearly face on. In other words, where you're looking more or less down the direction of the spin. So those also happen to be automatically the right angle configurations that we said we wanted, because you're looking down the spin axis, but then it turns out that the accretion disk wants to lie in the direction perpendicular to the spin axis. So emission from the accretion disk is automatically going to be in more or less this right angle configuration. But another nice feature of this configuration is that even if the emission in this right angle configuration, where you're looking down the spin axis of the black hole and the emission is coming from the equatorial plane perpendicular to that axis, even if the emission is a randomly varying signal that you don't know, so it's not a nice well-defined flash, but it's just random noise. The fact that you receive that random noise, identical copies of it in multiple delayed versions, means that even if all you know about the noise is that it has some peaked autocorrelation function, okay, which is this is the second figure here. So if the random noise is just correlated on short time scales and then the correlation dies away on long time scales, which is a typical thing, then the observed autocorrelation function will again have these extra spikes in it at these same time delays, just because even though the signal that's being emitted is totally random, it nevertheless perfectly correlates with the subsequent copies of that signal which reach you at slightly later times. Okay, so if I were to, so this I think is the realistic thing to go for. This is sort of the end of this part of the talk. The proposal is to look for either in stellar mass black holes where we have good X-ray timing measurements of them, or in supermassive black holes where there's actually a bunch of different wave bands that you might, where people collect data and you might hope to search for this, to calculate the autocorrelation function and try to fit to, so the autocorrelation function will probably be rather noisy, but nevertheless, if you have a predicted ringing signal to fit against it, then you can potentially draw this ringing effect out of the noise. Anyway, so that's the end. I wish I could tell you that this was already detected. It has not been, but sorry, did someone just? Oh, no question. So anyway, that's the proposal, so with that, I think I'll move on to the next. Okay, so the next part of the talk is, as I say, about something completely different. So any of you who have gotten completely bored of the previous topic and have glazed out, hopefully you'll like this one more. This is a project in progress, so basically, as I mentioned, there was this proposal, this is sort of one of the classic papers in early universe cosmology. It was this proposal by Hartle and Hawking in the early 80s for a formula for the so-called wave function of the universe. And so I'll try to explain to you briefly what that is and what one of its major problems is, and how a more recent paper, or two more recent papers on a completely different topic, there's sort of a mathematical technique introduced in these papers may be very helpful in solving that problem. Okay, so to warm up, let's look at one of my all-time favorite functions, the Riemann zeta function. This is the function. It's defined by zeta of s is defined by the sum over all integers from 1 to infinity of 1 over n to the s. And this sum converges when s is greater than 1. And then Riemann had the idea that you could, he thought to, Riemann loved to analytically continue functions into the complex plane, and so he thought about the analytic continuation of this function into the complex plane. So this is the complex S-plane here. So even though the sum only converges, so this is the real S-axis and this is the imaginary S-axis, and even though the sum only converges when the real part of S is greater than 1, basically in this red region, by extrapolating from the region where it does converge, you can analytically continue and obtain a unique function all over the complex plane. And you may know that that maybe the most famous outstanding problem in mathematics is the so-called Riemann conjecture, which is that, so if you ask what are the zeros of this function in the complex plane, well, there are some so-called trivial zeros that are equidistant, that lie on the negative real axis here and are equally spaced. But then there are the so-called non-trivial zeros, which are roughly speaking these things here, the points where these sort of colored tubes terminate. And they are observed to all lie on the line real part of S is equal to 1/2, but it's not understood why they all lie on that line. And so Riemann's conjecture is that there's an infinite number of zeros that all lie precisely on that line. My point is that this is a famous example of a function where the sort of thing that happens in complex analysis, where you have some function that you're interested in, and it's defined by a sum, but the region where that sum converges is not the region that you are actually interested in. So in this case, the sum converges over here, and you're interested in these zeros along a line in the complex plane where it does not converge. And you reach the place that you're interested in from the place where convergence happens by analytic continuation. So that's very analogous to the situation in quantum mechanics, where Feynman gave us this. Feynman gave a reinterpretation, a reformulation of quantum mechanics and how to calculate quantum mechanical amplitudes, involving a gigantic sum, analogous to Riemann's sum. Feynman's sum is his so-called path integral, but then again, the path integral at face value doesn't seem to converge very well, and so in practice, to interpret it, what one usually does is define the sum in a region where it does converge, get an answer then, and then proceed to the physically interesting regime by analytic continuation. So just to remind you, Feynman's proposal was that, or Feynman's reformulation was that if you have some initial configuration of a field living on this circle down here, living at some, this circle is my little schematic representation of all of space at the initial time ti, and then you want to know what is the amplitude for the field to have some different configuration, phi twiddle at t final, all over space at some later time. Then what you're instructed to do is consider all possible configurations phi of t that interpolate between the given initial configuration at ti and the given final configuration at t. And you do this gigantic summation, the so-called Feynman path integral, of e to the I times the action of that configuration, integrated over all possible interpolating configurations. Okay, and so here I've just shown the formula for the action for the sort of simplest field theory, the field theory of a single scalar field. So there's a kinetic energy term, there's a gradient term, and then there's the potential of the scalar field. And so again, basically, this is the action here. The thing inside the integral is a real number, and then and then you're taking e to the I of that and integrating it. So you have some wildly oscillatory integral that it's not clear what its convergence properties are. And so the standard trick that people do in ordinary quantum field theory, if they want to deal with the path integral, is they notice the following mathematical trick, that if we define tau to be I times the ordinary time, and we just rewrite this expression, and now we think of tau as a real variable instead of an imaginary variable, then suddenly it looks like we have a wonderfully convergent expression. I've just made the substitution tau is equal to IT here. So it looks like we have this expression that now is exponential of minus this thing in the integral, the so-called Euclidean action. And so now if tau is a real number, the action here would be some real positive number, and you're integrating e to the minus that, and it looks like some exponentially convergent integral. And so the idea, very analogous to the situation with the Riemann zeta function, is okay. Instead of what we'll do is instead we'll calculate the path integral in this Euclidean sense, where we take the initial configuration and the final configuration to be connected by a real Euclidean time coordinate tau. So we take this integral as if tau was real. We get a nice convergent answer as a function of tau, and then we get back to the answer we wanted, the Lorentzian path integral, by analytically continuing back to real values of t. Okay, so that's the idea, and that works beautifully in all non-gravitational field theories, basically involving scalar fields and spinors and gauge fields. But one wants to include the gravitational field, and so if you were to try to do that, you would be doing this path integral not just over the scalar field not just over the matter fields that interpolate between the initial field configuration and final configuration, but also over all of the possible so-called metrics that live on this interpolating space, this interpolating manifold, and that interpolate between the metric on the initial three-dimensional spatial surface and the metric on the final three-dimensional spatial surface. But now you're really doing something different, because I mean, as this metric really determines the shape of this space. So you can't think of this integral as taking place on a fixed cylinder or a fixed background, because different values of g in this integral correspond to warping and bending this intermediate manifold into different shapes. Okay, nevertheless, so Hawking, so there's another issue to contend with, which is that, so one of the main situations, I mean, there aren't really many practical situations in which you really need to do this integral involving the gravitational field. If you want to do quantum field theory on the Earth, you know, it's an excellent approximation to just leave the metric out of the whole picture. The situation in which you're really interested in doing this integral involving the metric is in cosmology. But then, you know, you run into a funny situation, which is that, well, so Feynman's proposal had the form, well, if someone tells me the initial state at time t initial, then Feynman's proposal tells me how to propagate that and obtain the wave function of the field at some later time. And you know, normally in laboratory physics, you know, maybe the experimentalist who sets up the system tells you the initial state. But in cosmology, it's not, you know, no one tells you the initial state. And in principle, one possibility is to just regard cosmology as a subject where we just have to assume some initial state and then say, assuming it was like that back then, what is it like today? But a more ambitious goal, a thing we could hope to do, is to try to ask whether maybe the laws of physics somehow determine this initial state. This is what the Hartle and Hawking proposal was. Hawking in particular noticed that once you include once you on the one hand have this idea that you're doing the path integral over Euclidean type regions where you've rotated t to I tau, or where you've taken tau is equal to IT, and you include metrics, you let the metric be one of the variables in the path integral, then you get into the situation where the metric, you know, the metric can curve the space in such a way that it matches on to the spatial surface that whose wave function you want to calculate, let's say today. But it doesn't require any prior boundary. The surface can bend so as to smoothly cap itself off, so in this case, you would sort of cleverly avoid the whole question of what was the initial state, or how do I have to assume an initial state or not? There's just no other boundary on which to specify an initial state here. Their proposal, in short, was to do this: that the amplitude of a given field configuration in metric configuration on a three-dimensional surface is simply given by the Euclidean path integral, the Euclidean Feynman path integral over all four-dimensional field and metric configurations that match on to the desired three-dimensional configuration, but otherwise are completely smooth with no boundary and no place where additional information would be required. And the paper is really very beautiful. It does a good job of explaining how, from various different angles, this is sort of a natural hypothesis to make about that this is a special state. But the problem now is that, well, when we do the path integral, we don't just do this path integral. We don't just do the path integral over the scalar field, or more generally over the matter field action, e to the minus the Euclidean matter field action. We have to include the action for gravity. And the problem when you do that is that, unlike with non-gravitational path integrals, where as I described for this one, this is a strictly positive number here. This action has a minimum that gives the dominant contribution to the path integral, and then all other contributions are exponentially suppressed. When you include the gravitational terms here, you end up with a Euclidean action that's unbounded both above and below. So there are no minimum or maximum configurations. There are configurations of arbitrarily large and arbitrarily small action contributing to this integral. So you get a horrible mess. The original idea was to rotate to Euclidean space in order to get a very well-defined path integral, but to get a nicely convergent path integral. But when you include gravity, that just completely goes awry. You get a horribly manifestly non-convergent path integral, worse than even the Lorentzian one. Okay, so that's the problem we'd like to fix. We'd like to somehow keep the elegance of this idea that somehow, if you really take the path integral to its logical conclusion and include gravity in it, that it can sort of cap itself off in a way that so that the Feynman path integral, in addition to giving you the dynamical law to evolve from one state to a later state, that it can also sort of select out a preferred state, and sort of obviate the need to make additional assumptions about initial conditions in cosmology. But we'd like to fix the convergence. And so, without getting too technical, so the point is that there were these papers by Ed Witten in 2010 that gave a very elegant idea about how to take a path integral and choose a manifestly convergent contour for that path integral, and it's different than what Hartle and Hawking wanted to do. So in other words, what previous people did to make their path integrals convergent was, well, the fields continued to take on real values. The scalar field phi continued to be real everywhere, but you took the time coordinate and rotated it to imaginary values. So here the idea is the opposite. What we're going to do is take the field values, complexify them, and then we need a prescription for how to choose. We want to let the action principle find its own contour through that space of complexified field values, find a natural contour on which the path integral will converge. And so that all is very abstract. And so rather than jumping directly to that, I was just going to give the zero-dimensional analog of Witten's idea. So So just consider this zero dimension. This is just an ordinary contour integral. Okay, we have some function here, exponential of I times some positive real number lambda times times a cubic polynomial in the z. Z is a complex variable, and we just want to do some contour integral over this integrand. So suppose we somehow wanted to let this integrand choose a natural non-zero contour for itself. Well, you know, the first thing you might think is, well, maybe I should choose some sort of closed contour, but since this integral doesn't have any poles, any closed contour that you integrated over will be zero. So what we want is instead some contour that runs from infinity somewhere in the complex plane to infinity somewhere else in the complex plane. And so what this diagram is showing is that if you want that contour, if you want to choose a contour that converges, you should choose it to go off to infinity in the complex plane in some region where the real part of this function is diverging to minus infinity. Because if the real part of the argument of the exponential diverges to minus infinity, that's saying that as you head off in that direction, the integral is converging very rapidly. And so, for example, for this function, because it's a cubic, there's three such regions. There are these three shaded regions where if you go off to infinity in those regions, the real part of this function goes to minus infinity, and then the three non-shaded regions are the opposite. The real part of the function goes to plus infinity. So you'll get a convergent contour as long as you connect any two of these asymptotic regions to any two of these asymptotic shaded regions to one another. And then what contour you pick, once you've chosen the two asymptotic regions that you're going to connect, what contour you pick doesn't matter. Cauchy's theorem tells you that whatever contour you take, you can make it wiggle as much as you want. As long as it starts over here and ends up over here, you're going to get the same answer. Okay, and so it looks like there are basically three independent choices, but if you think about it, if you add this choice to this choice to this choice, you get a closed contour that you can basically shrink to zero. So the sum of those three guys vanishes, and so you really only get two independent contours in this case. And the main point that I want to explain is that's not a coincidence. That's coming from the fact that this is a cubic function, and so its derivative is a quadratic function with two roots. And so the point is that Witten gives a nice explanation of how you can associate with every stationary point of this function. And in other words, every root of the derivative of this function, you can associate a contour with each such root. And so in this case, you do it by. So in this case, you'll get two roots that way. And so in detail, he does it by borrowing a technique from a branch of mathematics that I know essentially nothing about, called Morse theory. So all I know about Morse theory now is this one technique and so what do? You define h as the real part of the argument here, and now. Whereas we were thinking of this as a complex function over the complex plane, we now want to think of this real function, and we want to think of the complex plane as just a two-dimensional real plane with two real coordinates, x and y, instead of one complex coordinate, x plus iy. And so then once you have a function, once you have a real function over some real manifold like that, there is this thing called the Morse theory flow equation, which is this equation. So imagine I put down some Riemannian metric, some positive definite metric on my manifold. Then if I start at some coordinate xi, so some coordinate xy in my two-dimensional plane, then this is a differential equation that tells me where that point will flow to as I vary s. Okay, so in other words, I give you the initial value of the xi, of the xy coordinates in this plane. I give you this function h, and I tell you a metric on the manifold. And this is a one-dimensional differential equation that tells you where that point flows to. And so if I start at one of the critical points of this function and flow with this equation, what I get is a contour in the complex plane along which this integral is guaranteed to converge, a contour that runs off to minus infinity in both that runs off to infinity in the complex plane in two different directions, and the integral is guaranteed to converge on that because if you take dh ds along that contour and use the chain rule and then plug in this formula down here, you see dh ds is strictly decreasing away from the stationary point in either direction as you flow along this contour. Okay, so the point is now it's just a matter of there's sort of standard way that you take a one-dimensional integral and then generalize it to a multiple but finite dimensional integral and then generalize it to a infinite dimensional integral. This is a sort of standard, maybe not very mathematically well-defined technique, but this is sort of the standard way that, at least in physics classes, the path integral is introduced. And so Witten in his paper basically takes this idea and just does the analogous thing for the path integral. He shows, so here what we have is really just a fancy, he basically just converts this zero-dimensional or one-dimensional integral into an infinite dimensional integral analogous to the path integral. But beyond that, more or less just applies the same formalism to it. So he initially formulates the path integral over phase space. So here the x's stand collectively for all of the real coordinates on phase space. But then he complexifies those coordinates. He was basically interested in some mathematical topic that depended on doing a convergent path integral for a so-called topological field theory. But the point is that the idea is much more general, and it is in fact perfectly suited to solving this problem with the Hartle-Hawking wave function. In other words, the tentative prescription for the wave function of the universe is essentially just to apply Witten's idea to the gravitational to the action for matter fields plus gravity. So the advantage, a nice thing about this proposal is that it will automatically give finite convergent answer for the path integral, so it won't suffer from the basic problem that the Hartle-Hawking prescription does. But on the other hand, it defines a natural unique state as follows. So given a certain three-dimensional surface whose amplitude you want to configure, you want to determine, you simply find all of the saddle points of the action that match that surface, and then from each saddle point you use Witten's technique to use this sort of Morse theory flow equation to create a contour associated with that saddle point. And then the wave function would simply be the sum over all such saddle points, the path integral summed over all such saddle points. So in other words, that again, I hope the idea has gotten across. What it preserves about the Hartle-Hawking idea is that the path integral, once you specify Feynman's path integral prescription and the action functional, that the path integral finds for itself a natural contour to integrate over, which defines a natural state associated with any given three-dimensional metric and matter configuration. But it explicitly avoids the problem with the Hartle-Hawking prescription, which is the non-convergence. It's explicitly constructed to be a convergent path integral. And so in general, this will of course be an extremely hard thing to evaluate, but fortunately in cosmology, the universe is observed to be almost homogeneous and isotropic, very symmetrical, and especially the early universe is that way. And so for the so-called mini superspace of configurations that are nearly homogeneous and isotropic, evaluating this path integral and saddle point approximation and sort of the natural approximation is doable. And that's work in progress, but that's the basic idea. Anyway, thank you very much again.
Professor Boyle, I've got two questions. The first one is that you said that the intensity reduces by about 500 times. It reduces by so much. What I want to know is whether this is an empirical, thing which is known to you from your instruments, or is it a physical law, deterministic, which you know that it will have to be 1 by 500, or it's about that, so it turns out to be that, and you know the deviation, etc., etc. I want to know how.
It's a theoretical thing. So these highly bent rays have not yet been observed. There's no physical system in which we have ever observed a ray that is bent by more than a tiny fraction of 2 pi. But theoretically, you can analyze what Einstein's theory of general relativity predicts for such rays, and you can show theoretically that they are dimmed by this characteristic factor of e to the minus chi, where chi is the bending angle.
So whenever it is that you find some kind of a signal repetition which is falling down like this, then you know that it's a black hole echo phenomenon happening over here. You know that.
No, I wouldn't say that either. I guess there's other. If the echo that you see really fits this predicted profile, if you see several echoes and they dim and are delayed by the amount that you predict, then that gets to be quite compelling evidence. But you have to be very careful because these systems are messy, and so there could also be waves resonating in the accretion disk, or who knows what. There's things orbiting can cause kind of echoey effects, or apparent echoey effects, things orbiting in the accretion disk.
Professor Boyle, if there were to be signals that would just be repeating themselves after a constant delay, then of course they are different kinds of things. They are not this kind of thing,
yes,
of course.
Yes, that's true. That's right.